All right, hello everyone. Today is our exam 4 review, part 1. Today I'll be going over chapter 11, Alkynes, and chapter 12, Oxidation and Reduction. I'm going to be going over chapter 13 in the second part of this review, which I'll be doing tomorrow, which is Tuesday at 3 p.m. Eastern Time. And so I just wanted to split them up because I know chapter 13 is going to probably end up being sort of I shouldn't say a problem area, but something that gives you challenges more so than alkynes and oxidation reduction. So I want to make that a separate video for both my lecture and for you to go back and reference, okay? So if everything is good, we're going to start out with alkynes. So let's first talk about what alkynes are. So essentially what they are is when we talked about alkenes, those were carbon-carbon double bonds. Alkynes are carbon-carbon triple bonds. So let me draw the differences. So we have alkane, A-N-E, no double bonds, no triple bonds. Alkene, E-N-E, double bonds. Alkyne, Y-N-E, triple bond. And all of these are the same number of carbons. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. We just draw the alkyne slightly differently in order to reflect that these two carbons on either side of the triple bond are sp hybridized and thus will have a linear geometry. And so we draw that in our line angle structure. All right, and we can either have a terminal alkyne and an internal alkyne. And it's important to note that for the carbons that are part of the triple bond, they can only have one additional bond in addition to that triple bond. So if it's an internal alkyne, it will have 0 hydrogen bonds. However, if it's a terminal alkyne, it's either going to have 1 or 2 hydrogen bonds. And this will become more important later when we talk about something called an acetylide ion. And I know that concept comes up a little bit earlier than I want to talk about, at least in this chapter. So I'm probably going to end up skipping past that one portion and moving on to and come back to it towards the end. We're talking about more reactions, just as a sort of heads up there. Okay? So let's talk about naming these triple bonds. Essentially, we'll be naming these things very similarly to how we named alkenes. We give the triple bond the lowest number possible if we can, or if there's another substituent that's a higher priority. And let's talk very quickly about the different priorities. I'm going to skip past these examples, which we will come back to in a moment. So when we have more than one functional group, we sort of consider them to have different priorities. And essentially, this is just to avoid any inconsistencies with naming to ensure that everything named has exactly one name. So we don't say, oh, this alkyne is also an alcohol, so I'm going to name the alkyne first in this name, but I'm going to name the OH group first in another name. These priorities are meant to give names and unambiguous reference to an actual molecule. And you can see here the different priorities are pretty obvious. Alcohols, higher priority than thiols, higher priority than ethers, sulfides, etc., etc. The only thing that I need to add to this is the difference between alkenes and alkynes. So what if you have an alkene and an alkyne in the same formula? So like let's say we have this guy right here. Like this. So both of these have a triple or a double bond on carbon 2. So if this was carbon 2 referring to the alkene, it would look like this. If it's carbon 2 referring to the alkyne, it would look like this. And so in this case, we would say the alkene would be higher priority than the alkyne. But generally, they're considered the same priorities unless they were to somehow try to supersede another in one way. However, if there is a way to name things lower while also giving this double bond a lower number, that's fine. So like let's say that a double bond was right here instead of right here, we would want to start numbering from this end instead of this end, because that priority thing only really comes into play when they're both the same priority. Or not both the same priority, but they're both on the same type of carbon, like carbon 2 or carbon 3. And finally is alkanes. And then slight adjustment here, we also have halogens, so like bromo, chloro, all of that stuff. That comes before alkynes, that is one of the lower priority ones along with alkanes. And the way that I remember this priority stuff is if it comes later in the name, then it's more important. So for example, if I had an alkynol, like let's say that I have a let's say I have a 6-carbon chain with a triple bond somewhere and a alcohol group somewhere. I would name this hexinol. And we can see here that the OH group associated with the alcohols comes later in the name. And then the YN, which is associated with the alkynes, will come more recently in the name, I guess would be the word. And so we can see here that if we are later in the name, if we're later in the word, then our priority is going to be relatively higher. This is just sort of like a rule of thumb if you're having trouble remembering the different priorities. Like if you can't memorize this entire chart, this sort of rule of thumb might help you with naming things, at least on a test. Another example here would be, let's say we have a 5-carbon chain with a double bond and a thiol group. We would say this is a, what did I say, 5-carbon? Pentanethiol. I think that's how you spell it. I don't remember if you drop the E. I don't think you do, but I would look that up if you can. I just don't have it on hand for me, okay? And so now let's do some practice naming. Let's actually do this one right here. So again, we have a triple bond and a halogen. The triple bond will be a higher priority, so we're going to want to give that the lower number. So 1, 2, 3, 4, 5. So this is going to be a pentyne. So I'm just going to draw that. I'm going to write out that pair name. So this parent name would be pent, and then YNE because we have a triple bond. And then we see here, oh, we have a bromine on 5, and our triple bond is on 2. So we have 5 bromo, and some people will say 2 pentyne. You could also say instead pent2-ine, but both of these are correct, okay? I don't know which one's preferred. I think he once said that this bottom one is preferred, but don't quote me on that. I'm not 100% sure. Either way is correct though. Okay, and so then that's the gist of naming. So let's move on to the preparation of alkynes. So again, any reaction that you see here on this PowerPoint will be in the document that I've compiled with all the different reactions. But what's important here is to recognize that each of these chapters that we've been going over about these specific types of functional groups, it starts with something like, how do we make it? So if we want it, how do we make it? So we're going to start with something called a dihalide. And we mentioned this previously on our alkene chapter, but just to jog your memory, an alkyne or a dihalogen, or a dihalide, sorry, would be the word, is an alkane that has 2 halogen groups either on the same carbon or on neighboring carbons, okay? And the naming system goes like this. Geminal is sort of like Gemini. If you're familiar with the Western zodiac, a Gemini means twins. So geminal means these are twin chlorines, so they're gonna be on the same carbon. Bicinal, they're sort of in the same vicinity, but they're not twins like the geminal dichlorides or the geminal dibromides. Instead, they'll be on carbons right next to each other. And this is important. This is an important distinction because they have to be on carbons next to each other to do this sort of elimination reaction. Because let's think about it. To do elimination, remember we're eliminating 1 leaving group and 1 hydrogen. So if we eliminate 1 leaving group and 1 hydrogen, and we end up with a double bond right here, to do elimination again in that exact same place, we have to eliminate again on those same carbons, except this time we'll be eliminating from the leaving group from this carbon here and the hydrogen from this carbon to make our double bond right here, okay? It's the same thing up with this vicinal not vicinal, but geminal dihalide, except instead of having the halogens on 2 separate carbons, the halogens are on the same carbon, the hydrogens are on the same carbon. So what happens, we remove a leaving group, we remove a hydrogen, we gain a double bond. And then the second step, which is the second E2 reaction, remove a leaving group, remove a hydrogen, we end up with our triple bond. And that's overall how we make an alkyne. And this is sort of important. And we'll get to how do we make these dichlorides or these dibromides, how do we make these dihalides? Well, we'll talk about this a little bit when we get to some other reactions in this chapter. But what's important here is to note that to make an alkyne, we have to have a dihalide, whether it be geminal or vicinal, okay? Oh, and then to do that, to change that dihalide into an alkyne, we will do an elimination reaction twice. As you can see here, we're using a base or a strong bulky base. It doesn't really matter. Okay? All right, so let's scroll down. Okay, so this slide here is discussing the acidity of terminal alkynes. I'm going to come back to this later. For right now, I'm just going to continue on past this and move on to the actual additional reactions of alkynes. So a lot of these additional reactions should be at least a little bit familiar to you from the alkene chapter, because a lot of these have at least similar names, if not similar mechanisms. So we can see here, hydrohalogenation. Again, hydro means we're adding a hydrogen. Halogen means we're adding or halogenation means we're adding a halogen, okay? And similar to the alkene reaction, we are going to be using HX. However, instead of using a single HX, we're going to be using two equivalents or excess. Depends on how you say. We can say excess, like spelling up the whole word, or we can just do X apostrophe S, okay? But what you should note here is that, let's say that this is the first set of HX. To completely do this reaction, we need two sets, because we end up adding two sets of X and two sets of H, which comes from this 2HX. And another thing to note is that we'll be adding Markovnikov. And again, I'll explore this a little bit more when we talk about the actual mechanisms. But here we'll be adding Markovnikov in that, one, the hydrogen is going to add to the carbon with more hydrogens. And two, if there isn't a carbon with more hydrogens, then whichever carbon the first hydrogen adds to will be the carbon that the second hydrogen adds to. And it will make more sense when we talk about the physical or the actual mechanism, which we'll get into a few seconds. I just want to give you guys a brief overview of all of these, okay? Now the next one is also familiar because this is halogenation. Again, the name halogenation means we're only adding halogens, okay? And we can see here, again, similar to alkene reactions, we're using X2, but again, we're using two equivalents or excess of them, okay? And you can see here, Markovnikov doesn't exactly matter too much, because you can see here that no matter what we're adding two halogens on either side of that triple bond. So there's no Markovnikov addition, there's no E or Z, there's no chiral centers here, okay? And so now these next two are going to be a little bit more unfamiliar. We're still doing hydration like we did before, and we're still doing hydroboration-oxidation like we did before. But instead of ending up with an alcohol, we'll be ending up with either a ketone or an aldehyde. And again, we'll discuss it more when we get into the mechanism. This is just sort of an overview of all the different reactions that you can expect to see in this chapter as far as addition reactions go. Okay, and that's really important to note. These are called addition reactions because addition reactions are going from a pi bond to either 2 sigma bonds, or we're going from 2 pi bonds to 4 sigma bonds. And I'll discuss more why it's important to understand that these are the addition reactions in a little bit. I know it seems like I'm saying, oh, this will come back later, like a million times by now. But I just want you to understand, like, if you do have any questions, I will be coming back to them, okay? Okay, and so now this energy diagram sort of shows us the ways that the alkyne and the alkene differ as far as addition reactions go. So an alkyne is overall less stable, but it also has a larger difference in stability. So overall, an alkyne is less reactive than an alkene because its activation energy is much higher, okay? And so the difference in stabilities of the transition states is greater than the differences in stabilities of the reactants. So what that's saying here is that even though these seem very close in energy, the activation energy is going to be much different, okay? And so I don't think this slide is super important, but since he does mention it, I'm going to also mention that, okay? So now let's continue on to the addition of hydrogen halides. This is just halogenation, okay? And we'll get into the mechanism in the next slide. I just want to talk about the overall reaction scheme. So we see here in the first step, we add on that HX and then we make an alkene, where the H and the X are added either E or Z. And the reason why we're saying E or Z instead of cis or trans here is because we don't know what these R groups are. So we don't actually know their priorities. So we can't say definitively if it's going to be E or Z. And again, this has a little bit to do with the intermediate that we'll get in this first step. But again, that'll come up more when we talk about the mechanism in the next slide. Okay? And then in the second step, we go from the alkene to the alkane. So this reaction is much more familiar to us because we're going from an alkene to an alkane, doing an addition reaction where we add HX. Okay? So now note here, this is how we make a geminal dihalide. Okay, because remember, we said before that the hydrogens are going to end up adding to the same carbon, thus the halogens are forced to add on to the same carbon as well. So that means those halogens are on the same carbon. This is going to be a geminal dihalide. Okay, so this is how we would make a geminal dihalide. And I'm just going to take a quick detour here and talk about how do we make a vicinal dihalide. So if you remember in chapter 10, I know that feels like a billion years ago, but if we did the halogenation of an alkene, so like not H2, but like X2 here, we would end up having the X added to either side of the double bond, and then here is our vicinal dihalide, okay? So to make a vicinal dihalide, we do halogenation of an alkene. To make a geminal dihalide, we do the hydrohalogenation of an alkyne, okay? So that is how we make our two different dihalides, and that'll become a little bit more important when we do synthesis, which again comes back later in this PowerPoint, okay? Okay, so now let's talk about the actual mechanism of hydrohalogenation. So this mechanism should be pretty familiar to us, as with beforehand, we talked about with the alkenes, how the pi bond is first going to grab onto the hydrogen here. That hydrogen-bromine bond, hydrogen-halogen is going to break, and then we end up with a carbocation. And again, the more stable carbocation is the one that is more substituted. As a result, the hydrogen is going to end up adding to the less substituted carbon, aka the carbon with more hydrogens, okay? And then what happens is the bromine then attacks that positive charge, and we end up with our vinyl bromide, okay? And so then what happens is everything happens again. The double bond grabs onto the hydrogen as Markovnikov, hydrogen-bromine bond breaks, then the bromine attacks that positive charge from the carbocation, and we end up with our final product, okay? So again, this is very similar to the reactions we've done before, so it shouldn't come to, this mechanism shouldn't be super confusing to you. Again, ask any questions if you have them. All right, and so now this other part of this slide here is discussing the intricacies of the carbocation. So in the first step, it's pretty obvious like why we add the hydrogen to that particular carbon. We want to make the most stable carbocation possible, and the only way to do that here is to add the hydrogen to the carbon with less substitution on it. However, if we look here in the second step, we can get two possible carbocations. Again, we could say that A is the better choice because it's adding to the less substituted carbon, and thus the positive charge will be on a more substituted carbon and thus be more stable. But we can also look at this resonance structure that exists for A in particular, which means that A is stabilized by resonance and having that positive charge on that more substituted carbon, and that's why it ends up adding to the same carbon as the other hydrogen, okay? All right, so let's continue on. So that was hydrohalogenation. Next, we'll be getting into halogenation. So essentially, again, this is just like what we did with the alkene reaction, except we're doing it twice. The first step, the two of the X's add to the triple bond. We end up with an alkene, a trans dihalide, okay? And then double bond, and then we use X2 again, they add again to that double bond, and we end up with a tetrahalide, which essentially just means we have 4 halogens on our alkane, okay? And what's important to note here is that we're getting a trans dihalide. Note here how we're saying trans and not E or Z. And the reason why we're saying trans is because we can refer to this as trans because we're adding 2 of the same thing in opposite directions, I guess. So like this one would be up, this one would be down. Okay, and again, the reason we can say it's trans is because we're adding the same thing. And when we say cis or trans, at least with double bonds, we're talking about the same thing on either side of the double bond. So that means that this is always going to be trans no matter what these R groups are, unless the R groups are also a halogen. But that almost never happens, at least not in this case, all right? And so now we will see the mechanism. Again, this mechanism is relatively similar to the alkene halogenation that we've seen before, except now it's happening in 2 steps. Step 1, pi bond grabs onto the chlorine. One of the double bonds from the chlorine grabs onto the carbon that lost that triple bond. The chlorine-chlorine bond breaks. We end up with a bridged halonium ion. And if you recall, with bridged anything, epoxides, halonium ions, the reactant or the nucleophile is going to attack the less substituted carbon as well as a backside attack. In this case, attacking the less substituted carbon doesn't really make much of a difference, and I'll explain that why when we get to like the very end here. But then the nucleophile attacks that bond breaks, and we end up with our trans dihalide, and then the same thing occurs again. The chlorine is grabbed by the double bond, chlorine grabs on the other carbon, chlorine-chlorine bond breaks, chlorine attacks the one of the sides of the bridged halonium ion breaks, and we end up with a tetrahalide. And the reason why it doesn't particularly matter which carbon that this halogen here attacks is because we end up with a tetrahalide. And by design, or by the nature of the tetrahalide, it's going to have 2 of the same thing on either side. So no matter which carbon we attack, both carbons are going to end up with 2 halogens that are exactly the same, okay? Okay. And we can see here, this is a tetrahalide in reference to our dihalide from before, which had 2 halogens. And this is why we don't use this method to make a dihalide, because this isn't really a dihalide. This is a tetrahalide, okay? All right, so let's continue. And so now we're getting into more unfamiliar territory. So the mechanism itself is very similar until we get to this enol. And I'm just going to draw that mechanism very quickly right up here. So we start out with a triple bond. I'm just going to draw it like this. And we're going to be using an acid. I'm going to use H2SO4. Again, I draw it slightly differently in order to reflect that this bond here is the one that we're reacting with. Bond breaks, it's grabbed by that, and we end up with a positive charge over here or over here. It doesn't really matter because this is an internal alkyne. So both of the carbons on the alkyne are going to be the same substitution, okay? And so then what happens, H2O comes in, it attacks that positive charge, just like before. Let me use red. We end up with, sorry, I keep having to change colors. We end up with a positively charged oxygen next to a double bond. The positively charged oxygen is deprotonated, usually by the acid from before. Oh, this should be SO3H, not SO4H, sorry. Talking while I write. It attacks the hydrogen, the hydrogen bond breaks, and then we end up with a mechanism that is very familiar to us that we've done before, except now all we're doing is we're adding in an extra step with something called tautomerization. Okay, so I'm going to go ahead and clear this and scroll back down. So you can see here that we call our initial product an enol. And the reason we do that is because it's an alkene attached to an alcohol. And so the ENE, or the EN part, comes from this double bond. The OL part of the enol part comes from the alcohol. So we end up with an enol, okay? And so that's what we call it. And then what'll happen is it'll spontaneously tautomerize, that's the word, we'll talk about it in a second, into its other tautomer, the ketone, okay? And so the way that this occurs is usually we are going to be using an acid. Usually you'll see the acid that we start with when we do our hydration. In addition, you can see here that when we do hydration with an acid, with an alkyne, no matter what, we're going to end up with a ketone. Even if we have this, well, no matter what, if we had just 2 carbons here, it would end up as something else. But for our intents and purposes, most of the time, 99% of the time, it'll end up as a ketone. And you can see here, if we have a terminal alkyne, it'll end up as something called a methyl ketone. All that means is this here is just a methyl group, which is CH3, okay? And that's important when we talk a little bit later about the reaction of a terminal alkyne with a different reagent, okay? So now let's talk about tautomerization. So the reason we call this tautomerization is this is a sort of special reaction. Essentially, it's a reaction going between two constitutional isomers, but it's so special we gave these constitutional isomers a special name. They're called tautomers. So these two are tautomers of each other. So this is the enol tautomer and this is the keto tautomer. Obviously, enol name comes from this being an enol. The keto name comes from this being a ketone. And even though sometimes this form will not be a ketone, such as we'll see in future reactions, we're going to still call this the keto form, okay? Okay, so the way that this occurs is usually by acid, tautomerization in acid. There is a sort of tautomerization in a base, but that will come up more in organic chemistry too. For now, all you need to know is this tautomerization in acid, okay? And so what occurs is the double bond, just like all of the other times before, the pi bond is going to grab on the hydrogen bond breaks, we end up with a carbocation. Now that carbocation doesn't want to stay a carbocation, so what it does, it steals a lone pair from this oxygen, it creates a double bond. Now this oxygen doesn't want a positive charge, so what it does, it kicks the hydrogen out to be grabbed by the conjugate base from our initial acid here, and then we end up with our keto form. And overall, the keto form is more stable than the enol form, which is why generally you're going to see the tautomerization into this keto form, okay? And so you can see the whole process here. Addition of H2O to form an enol. Essentially, the hydration using an acid followed by tautomerization. Okay, so we can see here, grabbed by the pi bond, this bond breaks. We end up with a carbocation, which is grabbed by the H2O. The H bond is grabbed by the H2O from before. In this case, we are assuming that we're just in like a glass of water or something, but like just H2O is grabbing onto that other H, that bond breaks, we end up with an enol, and then the enol is going to react with an acid. We end up with a positive charge, this forms. Oops, I drew that arrow wrong. This leaves, grabbed by this, and then we end up with our final product. And so you can see here the actual, the end product of this, this hydration and acid followed by tautomerization, okay? And this is very important because if a question is like, what occurs after the hydration of this this alkyne using this acid or whatever, the answer would not be the enol, instead it would be the ketone, okay? All right. Somebody in the chat asked a question. I'm sorry, I don't know if I was late on this, but when would you use E or Z again? E or Z is used with double bonds. So let me do here very quickly. So remember, when we say E or Z, we're referring to double bonds that don't have the same thing on either side. So this would mean that we have like a chlorine on this side, a regular methyl group, and ethyl group on this side, and then hydrogen on this side. All these groups are completely different, so we can't really call them cis or trans, because again, cis or trans is generally reserved, at least for double bonds, for two things that are exactly the same. So like if instead this chlorine was a hydrogen, then yes, we could do cis trans, but instead we have to use E or Z. And somebody said HgSO4 is only added for terminal alkenes. I think you mean alkynes, but generally we are going to use HgSO4 in conjunction with H2SO4. I don't know why it's not written here, with alkynes. And this is just like for a stabilizing factor, but you can use it, you can forego using it if we're doing an internal alkyne, but generally you're going to want to use it if we are doing hydration using an alkyne. And the reason why it's added here is because we don't know what these R groups are. Okay, does that answer your question about when HgSO4 is used? Okay, perfect. All right, so let's clear this. I'm sorry I didn't see that question until just now. I had the chat window in a different monitor. Okay. So now we talked about hydration using an acid, and you may be wondering about hydroboration-oxidation because we also talked about that in alkenes. And generally, this process is going to work the same way as it did before. We're going to first use the BH3 to make the do the hydroboration part, and then we're going to follow with H2O2 and OH to do the oxidation portion. I'm not going to go ahead and draw the mechanism for this because it's a little bit advanced, and I'm trying to respect your time and my time. So if you really want to, again, you'll be able to look on my on my document that I made to see more about the hydroboration oxidation. But for now, I'm just going to skip it and talk a little bit more about what happens with hydroboration oxidation. So as far as the internal alkyne goes, everything is just about the same for this hydroboration oxidation and hydration using an acid. However, with the terminal alkyne, if you recall from back in chapter 10, when we do hydroboration oxidation, the hydrogen and the OH group, they're added anti-Markovnikov, which means the OH is going to be added to the less substituted carbon, in this case, the carbon next to the hydrogen, and the hydrogen will be added to the more substituted carbon. As a result, after tautomerization, we are going to end up with an aldehyde instead of a ketone, okay? But we're still going to sort of call it the keto tautomer, okay? So the biggest difference between hydroboration oxidation and acid catalyzed hydration of an alkyne is the final product for terminal alkynes, okay? And you see this R2BH. Generally, we just use that for stability sake. Usually you'll see I can never say this, but the dicyamyl borane or whatever. But generally, those R's are there to stabilize it. And if you see BH, it's just assume that you're probably going to be end up doing a hydroboration oxidation, okay? And so let's move on. So this here shows us the actual regioselectivity, which, reminder, it shows us which product we're actually going to get when we do the hydration of a terminal alkyne, or we do the hydroboration oxidation of a terminal alkyne. We can see when we do the hydration, we end up with a methyl ketone, and when we do the hydroboration oxidation, we end up with an aldehyde. And so that's the big difference between hydroboration oxidation and the hydration using an acid, okay? And so now we are going to be talking about acetylide ions. Go ahead and jump in with any questions that you have. I'm just going to continue on. So this whole concept of the acetylide ion is going to call back all the way back to chapter 2, I think it was, where we talked about acids and bases. So if you remember when we talked about acids and bases, we talked about something called REO, and what this means, atom, resonance, induction, and then orbitals, okay? What we're focusing on here is the orbital portion of REO, okay? And so what I'm going to do is I'm going to draw an alkane, an alkene, and an alkyne. So we have this, and then we have this. Let me just actually, okay. So each one of these is going to have a hydrogen. So here's the hydrogen for the alkyne, here's the hydrogen for the alkene, here's the hydrogen for the alkane. And if I asked you which one of these is most acidic, you should tell me it's this one. And if you don't remember, that's fine. Just recall that the hydrogen that is attached to this carbon, we're looking at whatever atom it's attached to and what orbital it has. So this one's sp, this one is sp2, and this one is sp3. And essentially the rundown is if you have more S character, the more acidic you are. So sp is going to be more acidic than sp2, which is more acidic than sp3. And so we can see here that when we have a terminal alkyne, we're going to have a pretty acidic hydrogen. As a result, if we take a strong enough base, I'm going to erase some stuff very quickly. If we take a strong enough base, then we can deprotonate this guy. So I'm going to move this over here. And let's say that I'm using NH2. And I'm going to give you the list of the strong bases you should know for this. But for now, I'm just going to use NH2 very quickly. So what will happen is the base will come over here, grab the hydrogen. Because again, acid-base reactions, the base accepts the hydrogen, the acid donates the hydrogen. And then what happens is this hydrogen-carbon bond will break, and then the electrons will go onto the carbon. And then we end up with something called an acetylide ion. I think we call this because it's an acetyl group has 2 carbons, that sort of thing. I don't have like a great way of remembering this, but this is just the acetylide ion, okay? And then, go ahead. Was there a question?
Sorry.
You're fine. Did you have a question or?
Yeah,
Okay.
it's from the one on the top very quick. So you said that when we're dealing with the sp3, sp2, or sp is the most acidic because it's a terminal, or because the way the hydrogen is bonded?
It's because of the way that the hydrogen is bonded. Because if you think about it, all of those things, we could consider them terminal if we draw them like this.
Right.
So like this here. The big difference between this triple bond here and then the double bond and the single bond is that hybridization. And I don't want to get too in depth about it, but the hybridization of that carbon is going to be more spherical than sp2 and sp3, which means it'll be able to handle more electrons a little bit better than sp2 and sp3. But the rule of thumb is the more S character you have, the more acidic you are. It's not because it's terminal alkyne. The only reason I drew it like this is because if I didn't draw it as a terminal alkyne, if you recall, then there would be no hydrogen, there would be no acidity, because we have to have a hydrogen to be an acid. Okay, does that make sense?
Yes, absolutely. Thank you.
Okay, no problem. Okay, so back to this concept right here. So we said that now we have our acetylide ion. So let's quickly talk about what bases can be used to make an acetylide ion. Generally, you'll see H minus in the form of NaH. You'll see NH2 minus in the form of NaNH2, or you'll see an R group. And this is one of the ones that is probably the trickiest, but the R group essentially means if we have an R group attached to a lithium, then it will be able to deprotonate that terminal alkyne. And essentially what this looks like is we have a carbon chain with a lithium at one end, okay? And so these are the main 3 bases that are strong enough to deprotonate and cause us to have our acetylide ion, okay? So why am I making such a big deal about this acetylide ion? Well, it's because we consider this acetylide ion a good nucleophile. So any reaction that we've done before with a nucleophile, we can do now with this acetylide ion, okay? So we can see here, we can do SN2 with an acetylide ion. We can do E2 with an acetylide ion. The important thing to note here is that we can only really do SN2 when we either have a primary alkyl halide or a secondary alkyl halide. If we have the tertiary alkyl halide, if you recall, we cannot do SN2 with the tertiary alkyl halide. So instead, it'll default to doing E2. Okay? And what's so important about this whole process with the SN2 in particular is because before now, we've never had a reaction where we can lengthen a carbon chain. All we've had is a way to change something on a carbon chain, to replace a leaving group or do something with it. Now what we can do is lengthen a carbon chain by increasing the carbon-carbon bonds, and this is called a coupling reaction. And the reason why it's called a coupling reaction is, well, because addition reaction was already taken up. Because if you recall, the definition of addition reaction is going from multiple or 1 pi bond to new sigma bonds. A coupling reaction is going from essentially going from 2 separate carbons to a new carbon chain between them, okay? And so then you'll sometimes hear people referring to this type of reaction as a coupling reaction, and that's what that means. And that's why it's sort of important to make that distinction between addition and coupling, because some people can get confused because, well, you're adding carbon. Why don't we call it an addition reaction? Because it's just not the definition of it. Okay? So let's continue on. And we can also see here that an acetylide ion, as a nucleophile, can also open epoxide rings. if you recall, whenever we have a nucleophile, we can attack an epoxide ring at the less substituted carbon by doing a backside attack, and then we end up with our nucleophile added to that carbon. In this case, our nucleophile is an acetylide ion, so we just have that end up with that connected to that carbon chain right there, okay? All right, so that is, I think, about it for the reaction-wise for this chapter. And let me swap over to a different screen very quickly. I think this is, yeah, so here is all of the different reactions for this chapter here. Again, this will be posted in the description of the YouTube video, as well as I'm going to try and push out that chapter 12 stuff, but we will see. But you can see all the reactions are here with at least a basic mechanism, okay? Somebody asked, does the nucleophile attach to the less substituted carbon chain with acetylide ions? Yes, because if you recall, whenever we do acetylide ion, and whenever we do a nucleophilic attack on an epoxide, that nucleophile is going to end up on the less substituted carbon. This is no different. The only main difference here is that our nucleophile is something that we haven't seen before. So it's just the same mechanism, it's just our nucleophile is just a little bit weird looking, okay? Does that make sense? Okay. So now we're going to talk about something called organic synthesis. So essentially what organic synthesis is they're going to give you a product, or they're going to give you your reactant, your product, and they're going to say, how did we get here? And so essentially we're going to do is the first step that I would like to do is I'd like to see, oh, here's my reactant. Is it very obviously in my product? And we can see here, yes, we can see that triple bond right here. Okay, sometimes it's not as obvious, but that's the first thing you should ask, because it can make the rest of the question a lot easier. So we can see here that we had that triple bond, so we added all of this. So what I'm going to do is I'm going to number that carbon chain 1, 2, 3, 4, 5, 6. So we added 6 carbons. We made a new carbon-carbon double bond, and the only way we know how to do that is with the acetylide ion. So the first step of this would be to deprotonate this guy with any base that you choose. I'm just going to use NaH. Then we end up with our acetylide ion. And then what we do is we introduce our carbon chain with its leaving group. So I'm going to say 1, 2, 3, 4, 5, 6, because we added 6 carbons in this final product. And so all I'm going to do is I'm going to add a leaving group. So Br right here. This leaving group can be any halogen. I'm just using Br because that's sort of the end-all be-all. But then we can see here that, just like before, leaving group leaves, the nucleophile attacks, and then we end up with our final product right here, okay? And I'm gonna give you guys a piece of advice that I wish I had known. Always number your reactants, your products, your in-betweens, your intermediates. Always number everything, just to make sure you're counting your carbons right and ensuring that you're doing the actual correct reaction rather than blindly adding on an extra carbon or not adding enough carbons, because that can cost you a lot of points. I don't know if that will cost you a lot of points on the test since it's online, but I know that on paper it will cost you a lot of points, okay? All right. And so organic synthesis is just essentially how I like to look at it. I like to look at it as just the culmination of all the reactions that we've learned up to this point. So you have all of the steps that you know everything that you need to know to do any synthesis problem that we ask of you, okay? So that means that anything that we ask of you will be within the realm of possibility for you to do. It's just some questions will be harder than others. And when we have a particularly hard question, sometimes we'll go through retrosynthetic analysis. All retrosynthetic analysis is we're doing synthesis, synthetic, backwards, retro. And so then we're going to use a special type of arrow to show this retrosynthesis, this arrow right here. This arrow means we're going backwards instead of forwards. So if I were to write this in a way, if I were to write this equation in a way that we're used to, the actual reaction would look like this, okay? So this type of arrow means forwards, this type of arrow means backwards. And each one of those arrows means like one step backwards. And so essentially when we do retrosynthetic analysis, we're taking things one step at a time backwards. I do sort of a combination of forwards and backwards analysis. It just depends on sort of your style, what you want to do with these retrosynthetic, with these synthesis problems. I know a lot of on your homework, in particular, it's going to make you do a lot of retrosynthetic analysis, but if you can do the whole problem on paper and then like describe it on your computer screen, you should be completely fine. It shouldn't matter which way you do it because you should end up with the same series of steps, okay? So let's scroll down and look at this question right here. So here's our first example of retrosynthetic analysis, because it can be kind of daunting to be like, oh, I don't know how to directly go from an alcohol to an alkyne. So instead, what we're going to do is we're going to think step by step going backwards. So how do I make an alkyne? Well, if you recall from the beginning of this chapter, we are going to need a dihalide to make an aldehyde, and we're going to do a dihalide combined with elimination E2 twice, okay? And if you recall, the two possible types of dihalides that we can have are a geminal dihalide or a bisenyl dihalide, okay? And so now what we're gonna do is we're gonna ask ourselves, okay, which dihalide makes the most sense for me to make? So if you remember, it's fine if you don't. If we look at this, we can see that when we make a geminal dihalide right here, we're going to start with an alkyne and then become a dihalide. Now in this sense, this doesn't make much sense, because if we're trying to make an alkyne, why would we convert an alkyne to a geminal dihalide just to go right back into an alkyne? So instead of using the geminal dihalide, we are going to be using the bisenyl dihalide. And again, if you don't completely remember all these reactions, that's fine. I would just do a lot of practice questions that have to do with these different equations. But so if you recall, to make a bisenyl dihalide, we are going to use an alkene with halogenation. So that means that we're going to use something that looks like this. And so the way that I sort of do these questions is every single step of the way, I ask myself, okay, can I get from my reactant to this particular product? If not, then I'm just going to go back another step. And I go, oh, can I go from this product to this product? If yes, then I'm going to sort of just start everything over, rewrite it as it's meant to be, okay? So if you recall, we can in fact make an alkene out of an alcohol by doing dehydration, okay? Does that make sense so far? I hope it does. And so now what I'm going to do, I'm going to rewrite all of this in the forwards direction with all the reagents listed. So I'm going to actually move this to the side just so I can remember it, because on the test you'll have like a lot of scrap paper, so you're allowed to do this, but let me see. Actually, can I make it smaller? No, I can't. So I'm just gonna put it like up here. It's gonna be slightly in the way, but it's fine. So we know that to go from an alcohol to an alkene, we have to do dehydration. We use H2SO4 or any strong acid to do dehydration. We end up with our alkene, okay? And then we're gonna do our halogenation of our alkene. In this case, I'm just gonna choose Br2, which then creates our dihalide. I almost drew another alkene, but that creates our dihalide, okay? And then what happens is we're gonna do elimination twice. I'm just gonna use the example that I used earlier with NaNH2, and then we end up with our final product, okay? So that is sort of retrosynthetic analysis, and then turn back around to be the actual equation, okay? All right, so I'm gonna clear. The rest of these slides are basically explaining what we just did. But there is, okay, so this here is sort of emphasizing the fact that there are usually multiple ways to go from one product or one reactant to the same product. Usually, since we're in sort of a theoretical position in a theoretical class, we are going to prefer the fastest route possible. So we're going to use all of the strong acids. We're going to use all the strong bases. We're going to use all of our dangerous chemicals that we like, because none of this is actually happening in like physical real life. However, sometimes when you have multiple routes, the longer route is preferred to in order to for safety, because again, the shorter route may make use of sulfuric acid, and sometimes you may think that using sulfuric acid isn't exactly the safest thing. So instead, you're going to go a more circuitous route to do something a little bit longer in order to keep everybody safe around you and to do the reaction. But in this class, we don't really have to worry about that. So generally, we're going to prefer the shortest route possible. And somebody asked, how much organic synthesis is usually on this test? That's a difficult question to answer, not only because I don't know what the test is going to be, it's also going to be online this semester. So I'm not sure how the translation from in-class tests to online tests is, because you have to remember that the online tests are generally going to be multiple choice. So I would say there would be quite a bit of synthesis, just because it's sort of the culmination of everything that we've learned thus far. And I would expect synthesis combined with oxidation-reduction, which we are going to be talking about in the next chapter. But overall, I would be prepared for any synthesis by really knowing your different reactions. Okay, let's move on very quickly. And so I'm going to pause the recording and allow people that are watching the video to try and do this themselves. Yeah. Okay, so that should have been enough time to at least get started on it. If you don't know where to start, that's fine, because this is a hard question, in my opinion, because it sort of combines everything that we learned in this chapter specifically. Now, to start here, I look, oh, here's my reactant. Is it obviously in my product? It's not obviously in my product. So instead, I'm going to think, okay, I start with a triple bond. Is there some way that this can come from a triple bond? Because yes, I know some of us know about oxidation-reduction, making ketones and all of that, but let's just pretend that we haven't actually learned anything about that chapter, and this is our first introduction to something like this. And so if we think about it, we think, oh, to make a triple bond into a ketone, we're going to have to either do hydration using an acid or hydroboration-oxidation. So in this case, I'm going to go ahead and number my carbons, 1, 2, 3, 4. And now I'm going to draw a line or whatever that represents my triple bond. And so now I'm going to ask myself, okay, am I going to do this with a terminal alkene or a terminal alkyne or an internal alkyne? So we can see here that this is a methyl ketone. So we can do either one, because remember, if we do hydration using an acid with a methyl ketone or with a terminal alkyne, we'll end up with a methyl ketone. So let's just go ahead and draw this really quickly.
So Casey, sorry.
What?
So to do this, we would do this with a terminal or with a
I'm about to show both ways.
Okay.
I'm going to show both ways, and I'm going to tell you the one that I prefer. So this is like an example of where we have two possible ways to do this, but one may be preferred over the other, and one may not. So here's our internal alkyne. I'm going to say this is our I. This would be our terminal alkyne, so this is going to be T. And so then our internal alkyne would look very similar, except it looks like this instead, so I. Okay? So either one of these could possibly be the alkyne that we use in order to do the hydration using an acid or hydroboration-oxidation. But one thing to note is that with this terminal alkyne, we can only do hydration using an acid. We cannot do the hydroboration-oxidation, because again, the hydroboration-oxidation of a terminal alkyne will end up being a aldehyde and not a ketone. This internal one, we can do either one. However, so let's think about it. So can we go from the triple bond to either one of these guys? The answer is yes. We can go to the triple bond to any one of these if we wanted to. It's just the number of steps for each one differs, okay? So let me just move very quickly. So let's say we have two triple bonds right here. One of them is going to become this guy right here, this terminal alkyne. One of them is going to become this internal alkyne. Either way would be correct. It's just one is going to be significantly shorter than the other. So both of them, again, to do a coupling reaction, the only way we know how to do a coupling reaction is to do the acetylide ion. So the first step is to make both of these into acetylide ions. So NaH, NaH, we end up with an acetylide ion. Negative charge, negative charge. And so then what we can do is say, okay, so if we're doing a coupling reaction, we know that we are going to be doing we're going to be doing some sort of replacer reaction. So let's compare these two. So we see that the triple bond right here is right here. The triple bond right here is right here. And so we can see here with the terminal alkyne T, we can see we have a 1,2 carbon chain on one side. So that means that we are going to be adding a 2 carbon chain with a leaving group to our acetylide ion, and then we become our terminal alkyne, okay? However, this internal alkyne has 2 methyl groups on either side. So we're gonna start with a methyl group, It's going to add on to that acetylide ion, and then we end up with one side of our internal alkyne, and then we have to do the acetylide ion again to make it into another acetylide ion in order to do another SN2 reaction with another methyl bromide, and then we end up with our internal alkyne. So we can see here that this process going to the terminal alkyne is a lot faster, a lot shorter than going into the internal alkyne. And that's why overall, I would say prefer the terminal alkyne over the internal alkyne in this case. It is not necessarily always going to be like this, but in this case, this is an example of where we have 2 possible routes, and we're just going to opt to take the shorter one because it's easier for us to write. Okay? So let's go ahead and select this, delete that, delete that. I'm going to go ahead and delete the internal alkyne as well. Okay. So now we have sort of a rough idea of where we're going. And now all I'm going to do is I'm going to rewrite this whole equation along with its reactants and fill out the whole thing as if it were, as if somebody was asking me, oh, how do I do this? Like, what is the process? So the first step, create the acetylide ion with a strong base. Second step, have a ethyl group with a good leaving group. We end up with our terminal alkyne. And then we're going to be doing hydration using an acid. So H2O, H2SO4, HgSO4, and then we end up with our enol. I know there's a lot. We end up with our enol, and then we're going to tautomerize using whatever acid we had before. Usually you would just go straight into the ketone. I just want to mention that the enol is formed. It just tautomerizes spontaneously into our final ketone. Okay? Does that make sense? Does anybody have any questions about that synthesis? Because what I did here is I took all of these reactions and I said, okay, here are the reactions I know. Here's how I know to get to a ketone. How do I get to, this is how I know to get to a ketone. How do I get to here from our triple bond? Okay? All right, perfect. All right, so somebody asked, how do we know whether to use geminal dihalide or the bisatyl dihalide to make an alkyne? So I'm going to go ahead and clear my screen very quickly. You probably have had enough time to either screenshot, pause, or write it down. So remember when we're making an alkyne, oops, that is not what I wanted. Remember when we're making an alkyne, of course we want some sort of halide. We want either a bisatyl dihalide or a geminal dihalide. So we can have like this or this. And I know it probably feels like it was like 50 years ago, but we talked about earlier in this review how to make each one of these. So we can make a bisatyl dihalide by using an alkene plus X2, whatever. However, to make a geminal, dihalide, we're going to need an alkyne plus 2x2. And so if our final results or our final goal is to make an alkyne, it doesn't really make much sense to go through all the trouble to go from an alkyne to a dihalide just to go all the way back to an alkyne. So that's why instead in that first synthesis problem that we talked about, we did an alkene instead, because one, we aren't being redundant, and two, we knew how to go from an alcohol to an alkene using the different reactions that we have learned thus far, okay? So it's just sort of a logic thing, because if you want an alkyne, why would you use it to make a geminal dihalide just to go all the way back to an alkyne if you already have one? So it's just sort of like asking yourself, does this actually make sense? And if so, then sure, go ahead. If not, then try to think about it in a little bit of a different way. Okay. So now we are going to go on to chapter 12, oxidation and reduction. So I personally really like this chapter. I think it's a lot of fun, honestly, because it has a lot to do with biochem, biomedical sciences, all of that stuff, because this oxidation reduction is happening all the time in our bodies. So I think it's really cool. Kind of a nerd for that, but it's fine. Okay. So somebody asked, did I have a sheet for this one too? Not currently. I'm going to be working on I'm going to work on getting it done before I upload this video so I can put it in the description. But I will make a note if I haven't. And I should be able to have it done tomorrow at the very latest. I'm doing my best though. Okay. So oxidation reduction. Before we talk about all this organic chemistry stuff, let's talk a little bit about Gen Chem. So if you remember in Gen Chem, we talked about oil rig. So oxidation is loss of electrons, and reduction is gain of electrons, okay? So that concept is going to sort of feed into here as well, but it's going to feed in a way that's sort of a weird way of thinking about it. So if you recall, we talked about earlier, I think in chapter 3 or something, we talked about how when we have an electronegative atom, such as oxygen, next to a less electronegative atom, such as carbon, it's going to pull that negative charge towards itself and make that carbon partially positive. We can also think of this as the electron density is being pulled away from the carbon and towards that oxygen. So if you think about it, this carbon is losing electrons. So it's being oxidized. So in organic chemistry, oxidation is sort of described as the increase in CO bonds or CZ bonds. And again, we mentioned CZ bonds because generally they're going to be more electronegative than carbon, because carbon is pretty not electronegative. So what that means is when we have CZ, generally the electron density around carbon will be less and it will be losing electrons, okay? And the opposite is true when we gain, or if we gain hydrogens, lose oxygens. Because hydrogen and carbon are not so different with their electronegativities, they're going to share electrons pretty well. They're not going to pull against each other, so the electron density is going to be staying relatively around the carbon and be just fine. So that's sort of how we connect the idea of the Gen Chem oil rig oxidation stuff and how we connect to the organic chemistry oxidation stuff. I always thought the organic chemistry definition was a lot easier, but this is just tying everything back together so you understand like where this definition comes from. It's not completely random, I promise, okay? So the more carbon-oxygen bonds we have, the more carbon-Z bonds we have, the less electron dense that carbon will be, and thus the more oxidized it is, okay? And the opposite is true when we have an increasing number of CH bonds, just like we talked about before, okay? So here are a few examples. This first example here would be oxidation, because we increased the 2 oxygen bonds, we lost 1 hydrogen bond. This would be reduction, because we lost 2 oxygen bonds and gained 2 hydrogen bonds. So what you need to look out for is if we are doing oxidation reduction or if we're doing neither. So like, let's say that we have a double bond, an alkene or something right here, and we do HBr. And so then we see here, we have an increase in carbon-hydrogen bonds, but we also have an increase in carbon-Z bonds. So the reduction, I guess, went up by 1, and the oxidation went up by 1. They went up the same amount, so they cancel out, and we consider this as a neither, okay? All right. So reducing agents. So right now we're going to talk about the different types of reducing agents that we have. And there, first off, is H2, which will probably be the one that you are most going to become most familiar with, because most of the reduction reactions will have hydrogen in them. The sodium borohydride, lithium aluminum hydride, the sodium and the ammonia stuff is going to be important to understand and sort of know about. But honestly, using H2 is probably going to be much more known to you. You're going to see a lot more, okay? Okay. So the first one we're going to be talking about, obviously, is going to be H2, as we can see here. So if we use H2 along with a metal catalyst, usually PED, palladium, cadmium, we can use almost any metal though, because essentially what's happening is this pi bond right here is being attracted by the metal. So it's like holding onto that pi bond right here. It's holding everything flat. So the hydrogens can come in and grab right there, and then be added to the same exact side. And then after that pi bond is gone, it's going to be released as a new alkane, okay? And so this will also happen with triple bonds, because again, remember, it's the pi bond that's being attracted to that metal. So if you go from 2 pi bonds to 1 pi bond, it's still going to be attracted to that metal. So it's still going to reduce all the way. And so this will be important when we talk about alkynes and reduction. I kind of skipped ahead there, but we can also use metal catalysts to reduce other double bonds. So we can reduce an aldehyde to a primary alcohol, or we can reduce a ketone to a secondary alcohol. Both of these are possible with this hydrogenation with a metal catalyst. And this is probably one of the more powerful reducing equations. So you have to be careful, like if you're trying to reduce something and not anything else, you have to pick and choose which reagents you use. And that'll be more clear when we talk about reducing a triple bond. So let's quickly go back just for a second and talk about the reduction of alkenes. So when we talk about the reduction of alkenes, we are either reducing the cis isomer in the sense that it is cis related to the hydrogens, or the trans isomer. And overall, the cis isomer is going to be holding more energy than the trans isomer because it's less stable, and things are higher in energy when they're less stable, okay? And so that's what this slide is talking about. And then now we're going to be talking about the reduction of alkynes. So like I said before, the pi bonds are what is sort of attracting that molecule to the piece of metal. As a result, until all the pi bonds are gone, it's going to stay stuck to that metal and it's going to continue reducing. And as a result, we're going to reduce all the way down to an alkane. However, sometimes you don't exactly want that. Sometimes you want to go to a specific type of alkene, such as a cis alkene or a trans alkene. And so we can see here that we have specific reagents that we can do in order to reduce an alkyne into a particular alkene, okay? And this type of thing is going to be more useful when you get into talking about Orgo 2 stuff, I think. We're talking about something should be in the cis position in order to do a specific reaction, or something has to be in a trans position to do a specific reaction. It just sort of depends on what kind of reaction that you want. But a question that's associated with this could be like, okay, how do I go from a cis alkene to a trans alkene? Because again, you can't freely rotate around a double bond. So to do this, we would first have to become a triple bond. and then go through this NaNH3 to become that new trans alkene. And again, a reminder, to go from an alkene to an alkyne, you're first going to halogenate the alkene, and then that dihalide is going to undergo elimination twice, and then you should have your alkyne, okay? All right, let's continue on. So now we're talking about the dissolving metal reduction. This one is less important than the other types of reduction, but essentially what's happening is, you see here, we have a sodium radical. We have a sodium radical, not a sodium without a full electron pair. So essentially what happens is it kind of donates its radical to one of these carbons, one of these bonds breaks, and we end up with an alkene with a radical on one side and an extra double bond, or not, but an extra lone pair on this side, which then will end up grabbing a hydrogen, and then we end up with a radical alkene. And then what happens is another sodium radical comes in, donates its other electron, and then we again get a free lone pair, and then the hydrogen comes in again, and then we end up with our alkene. So this one is less important than the other two, like the Lindlar's catalyst and the sodium in ammonia stuff, but it's still important to sort of recognize that it does exist. Okay. So, oops. Let's continue down. So reduction of polar CX sigma bonds. So essentially this is sort of like a replacement reaction. So remember when we did, we had these guys right here. This could be our CX bonds. Essentially what we're doing here is we're gonna replace that Br, or replace whatever our Z is, with a hydrogen, thus reducing it. And so usually we're gonna end up using LiAlH4, which is a very strong reducing reagent and will reduce almost anything it comes into contact with, okay? So we can see here that when we have an alkyl halide, the leaving group is gonna leave, this is gonna become H-, which is highly unstable and as a result is very reactive. So what happens is this is going to be attached here, and then we end up with Li plus X minus and AlH3, and then this reduced alkene right here. Okay, there's a more intense mechanism associated with it, but you guys don't have to know it. All right, let's continue on. So this is just continue on. This is the reduction of an epoxide, and essentially it's just an epoxide opening. We're using the hydrogen as the nucleophile, because again, we're using H-, very reactive, a very strong nucleophile. So all that is happening is a nucleophilic epoxide opening. The H attacks here, this bond breaks, we end up with O-, O- grabs a hydrogen from water, we end up with OH, okay? All right. Okay, so oxidizing agents. So we've gone past reduction, it's not that scary. And so now we're gonna be talking about oxidation. So our first oxidation is an O bonded to an O. And honestly, the most important concept here is the concept of a peroxy acid. If you see CO3H, that means we have a peroxy acid on our hands, okay? And the general formula for it looks like this, all right? Or we can have a metal attached to oxygen, which is KMNO4, OSO4, Ag2O, all of that stuff. And we'll get into that a little bit. And then we'll talk about PCC versus CR03. But the first thing we're going to be talking about is the O bonded to the O. Okay, the oxygen bonded to the oxygen. So I'm going to skip over this reaction chart here because I don't like it very much because it doesn't have the reagents on it. So epoxidation. So before, when we talked about making epoxide, back in the, I think, the alcohols, ethers, epoxides chapter, it said that we needed a halohydrate, which if you don't remember, that means we need an OH next to an X, or like a halogen or whatever. However, a lot of the times we don't have that, but we do have a double bond somewhere. As a result, we can use peroxy acid in order to make an epoxide and a carboxylic acid. What is also important to note here is that the peroxy acid is not a catalyst because it ends up changed into a carboxylic acid in the end here, okay? And so let's talk about that mechanism very quickly. So what occurs is something very similar to when we make the bridged halonium ion. The double bond grabs onto whatever we're trying to grab onto, in this case, the oxygen. A lone pair of the oxygen grabs onto the other carbon here, but we have to figure out what happens to the rest of these bonds. So essentially what happens is this hydrogen-oxygen bond is going to break, go onto the oxygen, and then it's going to be grabbed by this oxygen right here using one of its double bonds. And then this bond here is going to break and go onto this oxygen. And also, this oxygen is going to make a double bond right here. Okay, so there's a lot going on in this mechanism, but the most important part is this part right here. Everything else should fall in line, just like before. And if you're having trouble sort of visualizing how many, how these arrows are supposed to go, the way that I would do it, the way that I used to do it, like if I was confused, is I would count the number of electrons in each arrow. So each arrow has 2 electrons. So this one has 2 electrons, this one has 2, this one has 2. And we can see here that this oxygen here is going to end up with 8 electrons. 2 in lone pairs and 2 in bonds. Okay? And so you can see here that the two electron pairs that become bonds are this arrow and this arrow. And then we can see that the electrons that become part of a lone pair are in this bond, and then they also just exist on this oxygen, okay? And then we can see that this oxygen needs 8 electrons as well. So if it's breaking this double bond, it's going to make a new bond with hydrogen, have a single bond with hydrogen and a single bond with carbon, and so on and so forth. But all of these arrows are there for a reason because each oxygen, each atom should have a full octet by the time we get to the end right here. Okay. All right. So dihydroxylation. So again, the name here of this reaction is going to tell us all that we really need to know about the end product. Dihydroxy, we're adding 2 hydroxy groups, okay? And there are 2 ways that we can do dihydroxylation. The first way is anti-dihydroxylation, where we end up with a trans product. Or I guess you could say our OH groups will be on opposite types of wedges. And the reason why that happens is we first go through epoxidation, which we just talked about with the peroxy acid right here. And then we do a nucleophilic attack onto the epoxide that we've just created, thus doing a backside attack in order to create a dihydroxy, a diol, an alcohol with 2 OH groups, okay? So I think this isn't super hard, at least this concept, because 1, we know what a nucleophilic attack epoxidation will do in order to create something that has opposite wedges. Because obviously we're going to do a backside attack when we do epoxidation. I'm sorry, not epoxidation. We're going to do a backside attack when we're opening an epoxide. And so to make the epoxide, we're just going to do the epoxidation. Okay? All right. The one that I think is a little bit harder is the syn dihydroxylation, because there are a lot of different reagents that can do this. KMNO4 with H2O and OH, OSO4 with sodium HSO3 and water. I don't really have a good way of memorizing these other than they both have 4 oxygens. But just know that these reagents are going to do syn dihydroxylation, which means that's going to add 2 hydroxy groups on the same side versus when we did anti-dihydroxylation and we added 2 OH groups on opposite sides. Okay?
Question.
Right.
For the very quick for the so KMNO4 and then the OSO4,
Yes.
those are pretty much have the same characteristics as reagents, so they're going to create syn, always syn, and
they
adding.
have the same characteristics, but what's also important to note here is that the OSO4, this is going to undergo 2 reactions. one with the OSO4, and then the second one with this sodium HSO3 and H2O. Whereas with KMNO4, everything is going to happen at once. That's just something important to note because a lot of people forget that.
Happens at once. Okay, but they're going to create pretty much.
They're gonna create like the same type of product.
Same product. Okay.
Yes. Okay. Does that make sense?
Yes.
All right. Perfect. Okay. And so now there's one more way we can do this syn dihydroxylation, and that's using an osmium oxidant as a catalyst. So all this means is we have an osmium with a very high positive charge. So it's okay with gaining a lot of electrons or losing a lot of electrons because it already has that 8+. So it will be reduced at the same time as our alkene is oxidized. I'm gonna not focus on the sort of the, how do I say this? I'm not gonna focus on the mechanism here because it's not exactly important. Again, a lot of these mechanisms, at least in this chapter, are really, they're sort of extra information because we know all the really important mechanisms with SN2, with the acetylide ion stuff. It's just here they're so complicated, and you've already stuffed your brain with so many mechanisms. It can get kind of it can get a little overwhelming. Somebody asks, will anti-dihydroxylation pretty much always produce trans products? Will syn pretty much produce only cis products? Yes. I'm trying to think if there's anything wrong with that statement. I don't think there is. Don't think of them as cis and trans. Think of them as syn, they're added to the same side. Trans, they're added to opposite sides. But they should create cis and trans products. If, in the sense that the two OH groups, which are the same and thus can be considered cis or trans, they will, yes, okay, so I think that statement's okay. So they will be cis or trans. Cis with syn addition, trans with anti addition. Somebody asked, did we cover this in class? Yes, I think so. So here's an example. Provide the structure and the name of the product for the following transformation. This would be a good test question because it's combining, well, the test question would probably be, what is the name of this product after doing this reaction with it? And then you'd have like these bunch of different products on it. So I'm going to let everybody have a chance to do it. If you're watching the recording, pause it and try to do this on your own. Okay, so if you recall, OSO4 and the rest of these reagents are used for syn dihydroxylation. And we know that it's not going to be anti-dihydroxylation because we need a peroxy acid in order to do that. So let's draw our syn addition. All right, here's this guy, OH, OH, okay? And so we could also draw the product with these solid wedges being dash wedges, but since this is a meso compound, because we can see here we have a line of symmetry, we're just gonna draw the one, all right? So we're not quite done because now we also have to name this. Do you remember, does anybody remember what we change the suffix to when we have two OH groups? I feel like Dora. Yes, diol. So this is going to be a diol, okay? And so if you look at the parent chain, 1, 2, 3, 4, 5, this is going to be a cyclopentane diol. I'm going to add in the numbers in a second. I just want to reiterate that this is going to be the name overall. I just need to add the numbers, okay? We're not quite done because we also need to add cis to the front, exactly. So this is going to end up being cis, cyclopentane, 1,2-diol. Okay, and so again, this would be a good question because again, it's asking you to name it rather than draw it, which is adding like a level of difficulty. All right, okay, so let's continue on. Okay, so now we're getting into something called the oxidative cleavage. Oh, somebody asked, could we also use RS? You could, but cis-trans is much faster with these diol stuff. With this syn addition, syn dihydroxylation, anti-dihydroxylation. Cis and trans is just much faster, and I would use that with this. Just because this is like one of the rare cases where we're adding just OH as cis or trans. Okay, so oxidative cleavage of alkenes. One thing to note here, whenever you see O3, know you're going to be doing some sort of cleavage. And the way that I like to solve these is I see, okay, I'm doing a cleavage. I'm going to put a line down the middle of my double bond or my triple bond whenever we get to that. And now I'm going to number the different carbon chains on either side. 1, 2, 3, 4, and then AB. I'm just using ABC, and 1, 2, 3 just to make them very distinct from each other. You can use different colors, however you want, however this works. And so then what I'm going to do is I'm going to redraw both of these chains. So 1, 2, 3, 4, and then A, B, C. And then I'm going to be like, okay, my double bond was attached to 3, and my double bond was attached to A. So all I'm going to do is add a double bond oxygen to both of these, and then maybe lengthen it with a hydrogen to sort of show that. Okay? Honestly, oxidative cleavage is probably one of the easier reactions in here, just because all you have to do is sort of chop it in half and just keep the numbers straight in your head. Okay? One more thing we have to consider, though, with oxidative cleavage is if we are trying to go backwards. So if they give us the product and then they want us to find what our reactant was, we would do the same sort of thing. We would number each side. So I'm going to go ahead and redraw this as the aldehyde that it is. And so what we would do is we would just essentially just number things just like we did before. So 1, 2, 3, 4, 5, and A, B, C. Okay? And so now what I'm going to do is I'm going to draw the double bond, because I know if I did oxidative cleavage, then I started with a double bond somewhere. So I'm going to draw the double bond, and then I'm going to say, okay, carbon 1 was part of the double bond, carbon A was part of the double bond. So I'm going to say, okay, here's carbon 1, carbon A. I'm going to mark those 1 and A. And then we just end up drawing the rest of our chain. So 1, 2, 3, 4, 5, and A, B, C. Okay, you can finish numbering them out if you want to. 1, 2, 3, 4, 5. In fact, I would encourage that just to make sure that you're drawing the correct thing. You're making sure that you have the correct number of carbons. You're not adding, you're not dropping any. And one thing that I would note about this type of question is it could be the same type of question as before, where it's like name the reactant of this reaction rather than just draw it out. Okay? I wouldn't think that you would have to name something like this just because it's kind of intense, but do be prepared to name the reactants if they ask you to like figure out what they are. Just be prepared to name anything, honestly. Okay. So that was oxidative cleavage of alkenes. Now we're going to do oxidative cleavage of alkynes. So when we did oxidative cleavage of alkenes, we replaced a double bond with a double bond. And because oxygen can only do a double bond, we have to add in an extra bond here for the alkynes, because we start with 3 bonds. We have the oxygen taking up 2 of those in a double bond. So we make up that last bond in an OH group, making it a carboxylic acid. And essentially, we're just going to be doing the same process as before. So we split in half like this, and then we number each side 1, 2, A, B, C, and then we go over here and we say, okay, I'm going to draw it out over here. I'm going to pretend that the answers aren't already drawn out for me, but I'm going to say 1, 2, A, B, C, 1, 2, A, B, C. And so if I look here, I'm going to say, okay, I know that 1 was attached to the triple bond. So now that's going to be attached to a double bond oxygen and to an OH group. A was attached to my triple bond rather. So I'm going to add a double bond oxygen and an OH group. And so that's just generally how you do these. Just number them, make sure you keep everything consistent, and just I would recommend drawing these out or like rechecking your work. Like if you have time in a test and they ask you, oh, what are the possible products for this one? Draw out your products and then do the reverse reaction with your products to make sure that you're correct. Like what I mean by that is I say, okay, so I've numbered these 1, 2, A, B, C. I know 1 is going to be connected to A. So I'm going to have the triple bond right here. 1 is right here, A is right here, and then I'm going to have B, C, and then a 1, 2. And then I'm like, okay, so that matches my initial reactant. So these products are correct. I'm correct. I can put my answer in. Okay? Okay, also something to note, is if we have a terminal alkyne, we're going to end up with CO2 instead. And this sort of has to do with the fact that when we do this reaction, we end up with a C double bond O, an OH here, and an H right here. This is pretty unstable. So what's generally going to happen is these two hydrogens are going to pair up, and then this is going to become a double bond, and this is going to be CO2. All right? Okay. And there's more examples. Okay. So now let's talk about strong and weak oxidizing reagents. So strong oxidizing reagents are sort of listed here. Here are the strong ones. The weak one we are going to talk about is called PCC. And the way I like to think about these, as far as the alcohols go, I like to think of the strong oxidizing agents as able to reduce up to 2 times, whereas PCC, our weak oxidizing reagent, can only oxidize 1 time. Okay? And also another rule that we have here, when we're oxidizing, we cannot get rid of carbon bonds, but we can get rid of hydrogen bonds. Okay? So if we take this primary alcohol and we oxidize once, then we're going to keep one of our hydrogens, end up with a double bond to oxygen. So this would be PCC because we're oxidizing once. Okay? If we're using something like CrO3, KMnO4, any of these, then we're going to oxidize twice and replace the other H bond right here with another oxygen bond. So it's going to be R, double bond oxygen, OH. Okay? Okay. And so then this would be with CrO3. I'm just writing that one because that's the shortest one. Okay? And so then we look at this secondary alcohol. We see, oh, we only have 1 hydrogen, so we can only oxidize 1 time. So both of our strong and our weak reagents are going to create the same thing, a ketone. Okay? And then finally, we see with our tertiary alcohol, we have 0 hydrogens that we can oxidize. So we get no answer here, because it can't oxidize stuff, because it cannot oxidize a carbon-carbon bond. It can only really oxidize carbon-hydrogen bonds, okay? So that's sort of the big difference between PCC and CrO3, any of the strong oxidizing reagents, is that PCC oxidizes a primary alcohol into an aldehyde. Strong oxidizing reagents oxidize the primary alcohol into a carboxylic acid. All right. So this is just showing kind of what is happening when we use chromium trioxide and like some sort of positive charge. So some sort of hydrogen, some sort of proton donor. We end up with chromic acid, which is sort of what actually does the reacting. Again, this mechanism isn't as important as knowing the actual reaction, but we can see the mechanism right here. So our somebody said, what is a reactant for the secondary alcohol? PCC, we'll get into that a little bit later. That like on this side right here. So we can see here, here's sort of the idea of how the oxidation goes. Essentially what happens is this oxygen is pretty attracted to that electrophilic chromium. One of these oxygen bond breaks, we end up with this guy right here. And then we get a proton transfer where one of these oxygens, or not that oxygen, but the oxygen with the single bond grabs onto the hydrogen, hydrogen-oxygen bond breaks, we end up with this guy right here, okay? And then we have H2O, which then is going to protonate one of these other oxygens or take away a hydrogen from this other oxygen. It's going to take away this hydrogen and essentially sort of give it to one of the oxygens over here in order to do a proton transfer and make that final reagent. Again, this isn't super important because it's very complex. Just know like this general like step or this general scheme here. So this is a reaction scheme where it doesn't show any of the arrows. But essentially what's happening is the, how do I explain this? But essentially what's happening is the hydrogen, at the same time as this bond is breaking and being replaced by some other oxygen, is being grabbed by this H2O, and we end up with our ketone. Again, this, I wouldn't know this mechanism super well unless you're really into mechanisms. Okay, and so now we can see here, when we have PCC, I'm sorry, I misunderstood your question altogether. Back here, when I talked about the secondary alcohol, any one of our reactants, CrO3, KMNO4, PCC, any one of those will create a secondary alcohol into a ketone, okay? And this is because we're sort of oxidizing once, okay? Okay. And so we can see here basically the overall difference between using PCC and a strong oxidizing reagent. When we use PCC with a primary alcohol, we end up with an aldehyde. If we use a strong oxidizing reagent, we end up with a carboxylic acid. Again, I'm trying to get all of these reactants ready, put together in a document for you guys. You should be able to access it either in the description of this YouTube video or the next one at the very latest, okay? Okay. And here, again, you can see here that when we oxidize secondary alcohols, it just comes up with the same thing no matter if we use a strong oxidizing reagent or a weak oxidizing reagent. All right. And so then this is sort of the last concept for this chapter, but it is sort of a complicated one that he doesn't go over very in-depth in class. So I will talk about a little bit here. So let's say that we wanted to make an epoxide. That would be pretty easy, right, if we just use a peroxy acid. However, let's say that we wanted to make a specific enantiomer of a specific epoxide. To do this, we're going to have to use something called a sharpless reagent. I wouldn't memorize what the sharpless reagent is, just memorize the name and if it's plus or minus. Okay, that plus or minus is going to come into play a little bit later. Okay, so let's imagine that I have like a glass table or something, and I'm able to see like the double bond or whatever. So if you, let me draw this a little bit bigger. So if you remember, when we talked about double bonds, they're going to be sp2 hybridized, so they're going to lay flat on a table. And the way that I see that is going to be with a double bond right here, and then one of the bonds away from me, the other one away from me, one of them toward me, one of them toward me. So I've sort of turned this alkene onto its side in a way that its substituents are perpendicular to how we would usually see them, okay? And so then what we're going to do is we're either going to, A, use our sharpless reagent from above and sort of attach our OH group from above, just sort of bringing it down on top of that double bond, or we're going to bring it from below and sort of, go from below, attach it from below. This way, if we scroll up a little bit, we can see here that we're going to have different sort of stereochemistries depending on which way we add, from above or from below. And we add from above, we're using the minus sharpless reagent. We add from below, we're using the plus sharpless reagent, okay? So by using the sharpless reagent, we can control the stereochemistry of the enantiomer that we form using an epoxide, okay? Okay, and so I think there's more to it right down here. Yeah, so here's like a better drawing of it that I didn't do from before. And then we can see here the different stereochemistries. Let's look at this stereogenic center in particular. So we can say, okay, so here's the stereogenic center here. Here's the corresponding stereogenic center here. So now I'm going to give priorities. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so both of these have the lowest priority on the solid wedge. So we're going to go through what we did before with the how do I say it? With the tetrahedral. We're going to redraw everything for both of these. And then I'm going to say, okay, so here 1 will be on top, 3 will be to the side, 2 will be here, 3 or 4 would be here, and then 3 would be here, 1 would be here, 4 would be here, 2 would be here. And then all I'm going to do is I'm going to pick them up, move them around. And again, we're doing the same sort of concept that we did before in the stereochemistry chapter. So our 4 is going to move to our dashed wedge, our 1 is going to move to our solid wedge, and our 2 is going to move to our line. So I'm going to erase these very quickly. And then we're going to see, I'm going to do a different color so it's a little bit more clear. We're going to see 2 is right here, 1 is right here, 4 is right here. And then we can see our stereogenic center is going to be R. Okay, let's do the same thing up here. So 4 will move where 2 is, 2 will move where 3 is, 3 will move where 4 is. So again, I'm going to rewrite this. This is just good refresher on stereochemistry, just to make sure that you guys at least remember a little bit about how we did that. So 4 is here, 2 is here, 3 is here. Then we see here, 1, 2, 3, we are S. So we see here, the stereogenic centers are inverted, and this is due to that sharpless epoxidation because we controlled which enantiomer we made. And I think this is the last concept of chapter 12, oxidation-reduction. I know it's a little bit complicated, but I don't think there will be too many questions on it. There might be like 1 or maybe 2, but there are other questions in this chapter that are also really important to study. So if you're having trouble with this, I wouldn't get caught up on it. I would rather you go back and learn everything else in this chapter than get stuck on this and never learn anything else, okay? All right, so I think that's it for chapters 11 and 12. If there are any additional questions, I can answer them. If not, then I will let you guys go. And I will see you tomorrow or whenever, if you're watching it on YouTube, for part 2, which is going to be chapter 13, mass spectrometry and infrared spectroscopy. Okay? Spectroscopy. All right? Okay, I'll see you guys next time.